Have you ever pondered the fundamental laws that govern our universe? What if these laws behave differently based on where you are or how fast you're moving? Our universe is a grand tapestry, woven with mysteries that boggle the mind and challenge our understanding of reality. Its enigmatic nature has long puzzled scientists, triggering a relentless quest to decipher its workings. Classical mechanics and electromagnetism, two pillars of physics, seem to explain the natural phenomena around us perfectly. But there were inconsistencies, puzzling anomalies that couldn't be reconciled. These conundrums hinted at a deeper, more intricate design of the universe, one that demanded a new, revolutionary understanding. This was the stage set for a theory that would transform our comprehension of the universe, a theory that would reconcile the inconsistencies and shed light on the peculiar nature of space and time. Enter Albert Einstein, a scientist who dared to challenge the established norms. In 1905, Einstein introduced the special theory of relativity. He proposed two groundbreaking postulates that would change our understanding of the universe. The first, the principle of relativity, states that the laws of physics are the same for all observers, regardless of their relative motion. This means whether you're sitting still or jetting off at high speed, physics works the same for you. The second postulate, the invariance of the speed of light, asserts that the speed of light in a vacuum is always the same, irrespective of the motion of the light source or the observer. Picture a swift beam of light cutting through the cosmos at a constant speed, undeterred by the movements of celestial bodies. These two postulates lead to fascinating phenomena. One of them is time dilation. Imagine a clock traveling at near light speed. To a stationary observer, time on this clock appears to slow down. Yes, time itself can stretch and contract, and it gets slower as we approach the speed of light. Length contraction is another mind-bending consequence. Objects moving at high speeds appear contracted or shortened along their direction of motion to a stationary observer. Think of it as a cosmic squeeze where the universe appears to shrink for the speeding observer. Then there's simultaneity, a concept that challenges our understanding of now. Events that seem to occur at the same time for one observer might not for another, moving at a different speed. What's simultaneous to me might not be to you if we're moving relative to each other. Lastly, we come to the famous mass-energy equivalence, summed up in the iconic equation E equals mc squared. This tells us that mass and energy are interchangeable. A tiny amount of mass can be converted into a colossal amount of energy, and vice versa. Special relativity was revolutionary, but it was just the beginning. It opened up a whole new way of viewing the universe, paving the way for general relativity and our modern understanding of cosmology. It's a testament to Einstein's genius and the enduring power of human curiosity. 10 years later, Einstein expanded his theory to include gravity, resulting in the general theory of relativity. This theory revolutionized our understanding of gravity. No longer a mysterious force acting at a distance, gravity was now seen as the curvature of space-time itself, brought about by the presence of mass and energy. Picture a rubber sheet stretched tight. Place a heavy ball in the middle and it sinks, bending the sheet. This is a simplified way of visualizing how massive objects like the Earth or the Sun warp the fabric of space-time. Now let's talk about geodesics. In this curved space-time, objects move along the shortest paths, or geodesics. But to an observer, these paths appear as curves, leading to what we perceive as gravitational attraction. It's like a marble rolling along the warped rubber sheet, spiraling towards the heavy ball. Next, we have gravitational time dilation. Time, it turns out, is affected by gravity. Just as time slows down for objects moving at high speeds, it also slows down in strong gravitational fields. So, a clock near a massive object like a black hole would tick slower than a clock further away. This is not just theoretical. GPS satellites have to correct for this effect to maintain accurate timekeeping. Finally, there's frame dragging. When a massive object spins, it doesn't just warp space-time, it also drags it along. Think of a spinning ball in honey, pulling the surrounding honey as it rotates. This causes nearby objects to be pulled into the rotation, affecting their motion. These insights into gravity, space-time, and motion are not just abstract concepts. They have practical implications from predicting the orbits of planets to understanding the behavior of black holes. And they've opened our eyes to new phenomena like gravitational waves, which we'll discuss in the next scene. This new understanding of gravity opened up a universe of possibilities. General relativity made bold predictions, many of which have been confirmed by experiments. One of the most fascinating predictions of general relativity is the existence of gravitational waves. These are ripples in the fabric of space-time, created by accelerating masses. They travel through the universe at the speed of light, carrying with them information about the events that produced them. In 2016, the LIGO and Virgo collaborations made the groundbreaking detection of these waves, a century after Einstein predicted them. Then there are black holes, regions of space-time where the gravity is so intense, nothing, not even light, can escape. They were once just mathematical curiosities in Einstein's equations, but now we know they're real. In 2019, we even captured an image of a black hole's event horizon, giving us a direct glimpse of these mysterious cosmic beasts. General relativity also forms the backbone of our cosmological models. It describes the large-scale structure and evolution of the universe, from the initial singularity we call the Big Bang to the current expanding universe. The cosmic microwave background radiation, a faint glow left over from the Big Bang, was predicted by these models and later observed, further reinforcing the theory. Then there's gravitational lensing, a phenomenon where the path of light is bent by massive objects. This causes distant galaxies to appear distorted or magnified, and even allows us to see objects that are otherwise hidden behind massive ones. This peculiar effect was first confirmed during a solar eclipse in 1919, where starlight was observed to bend as it passed near the sun. And finally, general relativity predicts the existence of spacetime singularities, points where the curvature of spacetime becomes infinite. These are found at the hearts of black holes and at the very beginning of the universe. The theory of relativity has been validated time and again, reinforcing its significance. From gravitational waves to black holes, from the Big Bang to the cosmic microwave background, each confirmation of its predictions is a testament to its robustness and the genius of Albert Einstein. Despite its successes, the theory of relativity is not without its challenges. One of the most significant is the unification of general relativity with quantum mechanics. These two theories describe different aspects of the universe. General relativity provides an excellent description of the universe on large scales, like stars and galaxies, while quantum mechanics describes the universe on the smallest scales, such as particles and atoms. The challenge lies in developing a theory of quantum gravity that can reconcile these two seemingly incompatible descriptions of the universe. So, why is this important? Well, understanding quantum gravity could help us make sense of singularities, the regions of infinite curvature predicted by general relativity, such as those inside black holes or at the very beginning of the universe. It's like trying to read a book with missing pages. Quantum gravity could fill in those missing pages and give us a complete story of the universe. But it's not all theoretical. The theory of relativity also has practical applications that affect our everyday lives. Consider, for instance, the Global Positioning System, or GPS. The satellites that make GPS work are moving fast and are far from Earth's surface, which means both special and general relativity come into play. Special relativity predicts that the onboard atomic clocks on the satellites will tick slower due to their high speed. Conversely, general relativity predicts that these clocks will tick faster because they are further from the mass of the Earth. Without the corrections provided by the theory of relativity, your GPS device would accumulate errors of about 10 kilometers per day. That's the difference between you reaching your favorite coffee shop and ending up in the middle of nowhere. So, while we grapple with the challenges posed by the theory of relativity, we also benefit from its applications. It is a testament to the power of human ingenuity and curiosity. The theory of relativity continues to shape our understanding of the universe, while also driving technological advancements. Einstein's theories have left an indelible mark on the world of physics. His revolutionary thoughts on relativity have transformed our understanding of the universe, forging pathways for countless scientific discoveries. These theories have allowed us to comprehend the fundamental mechanics of our universe, from the behavior of light to the warping of spacetime around massive objects. The mass-energy equivalence equation, E equals mc squared, has become a symbol of modern science, encapsulating the profound insight that energy and matter are interchangeable. This concept has been pivotal in the development of nuclear energy and quantum physics. Furthermore, the predictions of black holes and gravitational waves, once only theoretical, have been observed, solidifying relativity's place in the pantheon of scientific truths. Relativity continues to challenge us, pushing the boundaries of our knowledge, enticing us to question and explore. As we continue to explore the cosmos, The theory of relativity will undoubtedly guide us on our journey, just as it has for over a century.